and that is to obtain regular expression for this finite automata. Again here there are three states, okay, that is q1, q2, q3, and q1 is the initial as well as final state. Okay, so we'll write equation in terms of q1, q2 and q3 by considering the invert transitions. So for q1 the equation will become 0 q1 plus q1 0. So the equation for this q1 will become q1 0 plus q3 0 plus epsilon, right? So we have equation for q1 as q1 0 plus q3 0 plus epsilon. Now for q2 there are three invert transitions, one from q1, another from q3, and third from q2 itself. So we get a equation for q2 as q1 1 plus q2 1 plus q3 1, right? Similarly we get equation for q3 as there is a single invert transition, so q3 will be q3 equals to q2 0. Okay, so these are the three equations that we have obtained, and now we want the equations in terms of q1 only, right? So let us see what substitutions we can do and how we can apply Arden's theorem. So you can see that here we have q3, and for q3 we have equation in terms of q2, so we can put this in q3 and get a equation in terms of q2, like convert this q2 in form of Arden's theorem, that is in the form r equals to q plus rp. Okay, so if we put q3 over here as q2 0, so we get the equation as q2 equals to q1 1 plus q2 1 plus q2 0 1, right? So in place of q3 we have placed q2 0. Okay, and now you can see that this q2 can be taken as common, so we get a equation as q1 1 plus q2 in bracket 1 plus 0 1, right? Now we have the equation in form of the Arden's theorem, that is r equals to q plus rp, right? And the solution to this equation is nothing but qp star. Okay, so we get q2 is equals to q and p star, so it is q1 1 in bracket 1 plus 0 1 the whole star. Okay, this is according to Arden's theorem. We have seen proof of Arden's theorem. Okay, now we get q2 in terms of q1, so here we have q3, so we need value of q3 in terms of q1 so that we can convert q1 in form of Arden's theorem. So what we do, we have q2 in terms of q1 and we have q3 in terms of q2, so you can put this q2, the value of q2 which is obtained over here, in equation q of q3, so that you will get q3 in terms of q1, which you can place over here and get and convert this q1 equation in form of the Arden's theorem, right? So let us do that. So we'll put q2, the value of q2 which is in terms of q1, in the q3 equation. Okay, so if we do that, okay, I have used first I have put this q2 over here, right? So one and the same way thing. So first I have put this value of q3 over here as q2 0, right? So you either do this way or do that way, one and the same thing. So what I have did, I have first placed value of q3 which is given over here in this place. Okay, so I got a equation as q1 equals to q1 0 plus q2 0 0 plus epsilon, right? So now this q2, we have q2 in terms of q1, so now we will replace this q2 by this equation. Okay, so either do this way or that way, one and the same thing. So we put q2 over here and we get a equation for q1 as q1 equals to q1 0 plus q1 1 in bracket 1 plus 0 1 whole star, and the remaining 0 0 as it is, plus epsilon. Okay, so now this q1 is common, so you can take this as common, and the equation becomes q1 is equals to q1 in bracket 0 plus 1 in bracket 1 plus 0 1 whole star 0 0 bracket close plus epsilon. So again we have obtained the equation in forms of the Arden theorem, that is r equals to q plus rp, and the solution to this is nothing but qp star. So q1 will be epsilon dot z in bracket 0 plus 1 in bracket 1 plus 0 1 whole star 0 0 the whole star this is according to the Arden's theorem, and epsilon into anything is the same thing. So we get a equation for q1 as 0 plus 1 in bracket 1 plus 0 1 whole star 0 0 whole star. So this is the required regular expression as q1 is our final state. I hope it is clear and you know now how to convert finite automata to regular expression. If you have understood,